Have you ever gazed up at the night sky, awestruck by the sheer vastness of the cosmos? For centuries, we believed atoms were the smallest, most fundamental units of matter. But what if I told you there's a deeper layer to reality, a hidden world beyond the atom? This is the realm of quantum fields, the fundamental building blocks of everything we see and touch. Quantum fields are like an invisible fabric underlying the universe itself. They govern the interactions of particles, giving rise to the forces that shape our universe, from the tiniest atoms to the largest galaxies. For centuries, physics focused on particles, electrons, protons, neutrons, as the fundamental building blocks of matter. Quantum mechanics revolutionized this view, revealing that particles are not so much tiny marbles as they are blurry waves of probability. Quantum field theory explains this by positing that particles aren't the fundamental entities we once thought they were. Instead, particles are merely ripples or disturbances in underlying quantum fields. Imagine dropping a pebble into a still pond. The ripples are disturbances in the water itself. Similarly, particles are disturbances in the fabric of quantum fields. Imagine a vast, invisible ocean stretching across the entirety of space and time. This is not an ocean of water, but an ocean of quantum fields, each one a symphony of energy and potential. Just as a symphony orchestra has different instruments playing different notes, the universe has different quantum fields, each one responsible for a different type of particle. These fields are not static, they're constantly fluctuating, vibrating with energy, a cosmic dance of creation and destruction. These ripples are like particles, fleeting disturbances in the underlying field. Quantum fields can interact with each other, giving rise to the forces we observe in the universe. Quantum field theory, or QFT for short, is our best attempt to understand this hidden world of quantum fields. QFT emerged from the marriage of three of the most successful theories in physics: classical field theory, special relativity, and quantum mechanics. QFT weaves these three pillars of physics into a single, coherent picture, providing a framework for understanding the universe at its most fundamental level. It's a theory that has been tested and verified time and time again, with predictions matching experimental results to astonishing precision. But QFT is not just about explaining what we already know. It's a tool for making new predictions, for pushing the boundaries of our understanding of the cosmos. One of the most profound implications of quantum field theory is that particles are not eternal, unchanging entities. They can be created and destroyed, popping in and out of existence like fireflies on a summer night. This constant dance of creation and annihilation is a fundamental feature of the quantum world. In quantum field theory, particles can interact in a similar way. When two particles collide, they can bounce off each other, or they can annihilate each other, disappearing in a burst of energy. This constant interplay between energy and matter is at the heart of quantum field theory. In the world of quantum field theory, it's not the particles that take center stage, it's the fields themselves. These fields are the fundamental ingredients of the universe, the very fabric of reality. This cosmic jelly is the quantum field. It's not something we can see or touch directly, but its presence is felt through the particles that arise as disturbances within it. The field itself is always present, even when there are no particles, just as the water is always there, even when there are no ripples. So, if particles aren't the fundamental building blocks we once thought they were, what are they? In quantum field theory, particles are viewed as excitations or vibrations of the underlying quantum fields. They're like ripples in a vast, invisible ocean, fleeting disturbances that carry energy and momentum. Think of a guitar string. When you pluck the string, it vibrates, creating a sound wave. Similarly, a particle is not the field itself, it's a disturbance that propagates through the field. The electron field, for example, is responsible for electrons, while the electromagnetic field is responsible for photons, the particles of light. These quantized vibrations correspond to the different types of particles that we observe. One of the most counterintuitive aspects of quantum field theory is the idea that empty space, the vacuum, is not actually empty at all. Instead, it's a seething cauldron of quantum activity, filled with virtual particles popping in and out of existence. These virtual particles are not directly observable, but their presence has real, measurable effects. The Casimir effect is one of the most striking experimental confirmations of quantum field theory. Imagine trying to bake a cake without a recipe. That's where the Standard Model comes in. It's the recipe book for the universe, a comprehensive guide to the fundamental particles and forces that make up everything we see around us. This quantum recipe book doesn't list ingredients like flour and sugar, but instead lays out the fundamental building blocks of matter quarks and leptons. Quarks form protons and neutrons, the heart of every atom, while leptons, like the electron, are more solitary. The Standard Model describes three fundamental forces: the strong force, the weak force, and the electromagnetic force. The Standard Model isn't just a random collection of particles and forces, it's built upon a foundation of elegant mathematical symmetries. These symmetries dictate how particles interact with each other and how forces behave. In the Standard Model, symmetries are so fundamental that they give rise to the very existence of certain particles. For example, the Higgs boson, the elusive particle that gives other particles mass, is a consequence of a broken symmetry in the Higgs field. The Standard Model has been incredibly successful in explaining the behavior of the universe at its most fundamental level. But like any good recipe book, it has its limitations. The Standard Model doesn't include gravity, the force that governs the large-scale structure of the universe. Then there's the mystery of dark matter and dark energy, invisible substances that seem to make up the majority of the universe's mass and energy. These gaps in our understanding suggest that the Standard Model, while incredibly powerful, is not the final word on the nature of reality. It's a stepping stone, a crucial chapter in the ongoing story of our quest to understand the universe and our place within it. Quantum field theory has revolutionized our understanding of the universe, yet it leaves one significant gap: gravity. Despite the successes of the Standard Model, gravity remains stubbornly outside its grasp. This is because gravity is described by Einstein's general theory of relativity, which is a classical theory, not a quantum one. General relativity describes gravity as the curvature of space-time caused by mass and energy. However, when we zoom into the microscopic world of quantum fields and particles, this description breaks down. Theoretically, gravity should be mediated by a particle called the graviton. But merging quantum mechanics and general relativity into a consistent theory of quantum gravity has proved to be one of the greatest challenges in theoretical physics. Understanding how gravity operates at the quantum level is crucial for a unified theory of everything, which would seamlessly integrate all fundamental forces. Apart from gravity, quantum field theory also struggles to explain dark matter and dark energy, two mysterious components that together comprise most of the universe's mass-energy content. Dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. On the other hand, dark energy is an even more enigmatic force driving the accelerated expansion of the universe. Quantum field theory has yet to provide a satisfying explanation for dark energy. One hypothesis is that it could be related to the vacuum energy predicted by quantum mechanics, but calculations of this energy differ wildly from observed values. Discovering the true nature of these invisible forces could revolutionize our understanding of the cosmos. Quantum field theory, despite its successes, is riddled with mathematical challenges. Its calculations often involve infinities that need to be renormalized to produce finite results. While renormalization is effective, it is not mathematically rigorous, raising questions about the theory's fundamental consistency. Haag's theorem, for instance, points out inconsistencies in the interaction picture used in quantum field theory, suggesting that our current methods may need revision. Meanwhile, the Yang-Mills existence and mass gap problem, one of the Millennium Prize problems, highlights the need for a better mathematical foundation for quantum field theory. To address these issues, physicists are exploring non-perturbative methods and alternative formulations of quantum field theory. Lattice QFT, for example, provides a discrete framework that can handle strong interactions more rigorously. Additionally, axiomatic approaches aim to establish a more solid mathematical foundation for quantum field theory. The quest to understand quantum fields continues to push the boundaries of both physics and mathematics. Future directions include integrating quantum field theory with quantum gravity, uncovering the true nature of dark matter and dark energy, and refining the mathematical underpinnings of the theory. As we look deeper into the fundamental fabric of the universe, these efforts promise to unlock new realms of knowledge and transform our understanding of reality itself. As we've journeyed through the subatomic world, from the familiar terrain of particles to the ethereal realm of quantum fields, we've uncovered a universe far stranger and more wondrous than we could have imagined. Those twinkling stars, scattered across the night sky like diamonds on black velvet, are no longer distant, unknowable objects. They're echoes in the quantum fabric, their light carried by ripples in the electromagnetic field, a symphony of energy that has travelled across billions of light years to reach our eyes. The air we breathe, the ground beneath our feet, even our own bodies, are not the solid, unchanging structures they appear to be. They're dynamic, ever-changing manifestations of quantum fields, a swirling dance of energy and information. Every atom in our bodies, every grain of sand on the beach, is a testament to the intricate interplay of quantum fields, a cosmic ballet choreographed by the laws of physics. The journey into the quantum world is not just about understanding the universe out there, it's about understanding ourselves, our place in the grand scheme of things. We are not separate from the universe, observing it from afar. We're an integral part of it, interwoven into its very fabric. But our journey is far from over. Quantum field theory, for all its triumphs, is still a work in progress. The search for a unified theory of everything, one that can weave together the forces of nature into a single elegant picture, continues to drive physicists to the frontiers of knowledge. The enigmatic nature of dark matter and dark energy, those invisible forces that shape the destiny of the cosmos, beckons us further into the unknown. Are they particles, fields, or something even more exotic, challenging our very notions of what constitutes reality? And what of the elusive graviton, the hypothetical particle that would carry the force of gravity into the quantum realm? The mathematical challenges of quantum field theory, the infinities that lurk in its equations, hint at a deeper level of understanding yet to be attained. Perhaps there's a more fundamental theory, one that can encompass the weirdness of the quantum world without resorting to mathematical sleight of hand. The universe is far more complex, far more interconnected than we ever dared to imagine. The quantum world is the very foundation of our existence. Quantum fields have the potential to revolutionize our world. From quantum computing to advanced materials, to a deeper understanding of nature's laws and new insights into the human brain, the applications look really interesting.